Hi everyone, welcome back to the Bioinformatics Code channel. In today's video, I'm going to show you how you can perform variant calling on the Galaxy platform using BCFTOOLS. This video was made using this Galaxy tutorial here. This is the page and I will leave the link to this page in the description box so you can check it out. So this is the workflow we are going to use. Let's scroll down and then we'll see the workflow. We are first going to get our FASTQ files. Okay, that's the sequence reads, and then we are going to align the reads to the reference sequence, and after that we will perform the variant calling. I am skipping quality control and then alignment cleaner because the focus of this tutorial is to show you how to perform variant calling using BCFTOOLS. But if you are going to call variants using your own data, it's advisable you perform quality control and also do the alignment cleanup. Okay, so that's something that you have to do. I've covered some tutorials where I showed how to perform quality control and also how to do the alignment cleanup. So you can watch those videos as well. The links to those videos are in the description box. So just make sure to check them out. Okay, so that's about it. So this tutorial here uses the command line versions of the tools we are going to use, but we are going to run everything using the Galaxy platform, so you don't need to have a programming experience or programming background, so take note of that. So the first thing we have to do is to get the example data. So let's check the data. So we need the FASTQ file. So this is the link. Okay, so if you want to use the command line to download, then you can use curl to do it, but you can also use your browser. I will use my browser to download it. So I will just highlight it and then open this link. So I'll open the link here. So once you open it, you'll be asked to save the file. So I'll save it as it is, okay, on my PC. So I'll save it and then I'll go and then check the file. It's a tarball. That means that it's compressed. So we are going to look at that file and then extract the contents. So let's go and then check the file out. So I'll open the directory which has the file, and this is it. So here I can open it and then check the contents. This is it, but I want to extract, so I'll just extract it here. Okay, I have extracted the content, so I'll open it and then check what's there. So I have some FASTQ files. So that's what we are going to do. We are going to use just one sample. Okay, that's what we are going to use. But let's check the Galaxy tutorial and see the exact files that were used so that we can also use them. So on this page, just scroll down to the mapping section here. So let's check the file. Okay, so we are using this sample here. Okay, we are dealing with paired end reads. So each sample will have two files, the forward and the reverse sequences. So we are using this particular one here. So let's go and then check that sample out. Okay, so these are the files that we are going to use. So take notes. So what we are going to do next is to go back to the Galaxy platform and then upload this file. So let's go back to the platform. Okay, so we are on the Galaxy platform. So the first thing you have to do is to create a history. That's what you have to do first. So to create a history, you need to first sign in. Okay, if you have not signed in, make sure you have signed in. If you don't have an account, make sure to register and get an account. After that, you can create your history. So I will create mine here. So just follow my cursor, come to this side and then click on this plus button here. So once you do that, you have this coming up. So you can edit it and then give it an appropriate name. I'll use variant calling. This is the name I will use. So I will save it. Okay, now I am going to upload my files. So I'll come to this side. I'll click on upload data and then I'll upload my file. So here I'll use this one, choose local files. Okay, that's what I'll use. I've already covered some tutorials where I showed how to upload files to Galaxy platform. There's one particular tutorial where I showed 3 different approaches. So if you want to learn more about file uploads, you can check that video out. The link is in the description box. So let's use this one. We are going to upload the files from our PC. So we need to select the choose local files. So I'll click here and then I'll go and select the file that I want. I'm using this one, this, and then this. Okay, so that's a read 1, read 2. So I'll select both. So this and then this. These are the ones I'll use. So I'll open them. And then once I do that, I'll have them appearing here. After that, I'll click on the start button here. So I'll click it and then the file upload will commence. So once we have this, we should also see some files on this side. Okay. So once you see the files here, that means that the files have been uploaded. So here, I think it's the preparatory step. So let's wait for the files to upload. So if the status here gets to 100%, you can close it. So let's close this one. Let's close the window. Okay. You should also see some files here. Okay, 2 of them. So we should see them here. Okay, the files have been successfully uploaded, and that is why the background of the names are green. So let's go back to the upload data button. Let's click it and then we can reset this and then close it. So now everything is ready. The next thing we do is to perform the genome mapping. We are going to map the reads to the reference sequence. So let's proceed. So if you take a look at the Galaxy tutorial, mapping was done using BWA. Let's take a look. Yeah, mapping was done using BWA mem. So we will also do the same. So let's go back to our platform here and then we'll search for BWA mem. So let's search. We say BWA mem. So we should see it here. So let's use this one here, BWA mem. So we will select it and then proceed with the rest of the activity. Now, before we proceed, let's go back to the tutorial. So in the tutorial here, the reference sequence was downloaded and then an index was generated, but we are not going to download the reference sequence. We are not going to generate index. The Galaxy platform already has a built-in genome index that we can use. So that's what we'll use to perform the genome mapping. So let's select the parameters. So here we have use a built-in genome index. That's what we are going to do. So we will maintain this. When we come to the reference genome, we will select the E. coli one. So let's click it and then scroll down to search. You can also type, by the way, but I prefer to scroll down and then get them. So we'll use this one here, the E. coli string K12. So select it and then scroll down. So here it's asking whether we are using single or paired entries. We are using paired entries, so we will maintain this. If you don't see this, click and then select paired. Now it says select first set of reads and then select second set of reads. So here I need to select the forward and then the reverse. Okay, so the first one is the forward, the second one is the reverse. So you should see this. If you don't see this, if you don't see 1 and 2, just make sure you select them. So here I already see 1, but I'll show you how to select. So you can come here and then click and then you can select the one that you want. And then when you come here, that is the reverse. It should be the 2. So click again here and then select the 2. That's the reverse. So you should have 1 and then 2. Okay. Now here it says set read groups information. Okay, so read groups are important, okay, but for this tutorial I will not set it because we are using one sample, and then a BCF tools does not require us to set read groups. But if you have multiple samples, then it's advisable to set the read group because it will help you to process your data. There are a number of things you can do if you set read groups. That's basically what I'll say. So you need to set read groups if you are dealing with lots of samples, and also some variant callers require that you set read groups. For example, GATK will require you to set read groups, okay, because it's using that information for processing. But for this tutorial, we are not going to set any read groups. So let's proceed. So we will maintain this. Here it says select analysis mode. So here we are using simple Illumina mode. That's what we will use. So make sure you set that. And then when you come to BAM sorting mode, you maintain this one, sort by chromosomal coordinates. Make sure it's set to this. So here we are performing the mapping, and then we are also sorting the alignment records. Okay, if you're using the command line version of the tools, you need to first perform the mapping, and then you also have to sort. But when we use the Galaxy platform, everything is given here, so you just have to select them, and then they will be done for you. So that's about it. So now we have everything we need. We have selected our parameters, and so we can click on the execute button to start the genome mapping. So let's click it and start the mapping. So click it now, and then the job will be submitted. Okay, so here we have the tool that is being used, or the command that is being used, and then we also have the input files. We have 1 and 2, that's the forward and the reverse, and we also have the output file that will be generated, the outputs. Okay, so the outputs here is what will be generated. This is in the BAM format. Okay, so we are going to generate this. So once the job has been submitted successfully, if you check the right side, you will see the outputs also displayed here. So if the background is gray, that means that the job is in queue. Okay, so if the background changes to orange, that means that the job is processing, and if it turns to green, that means that the job has been completed. So let's wait for the job to complete. Okay, mapping has been done, so let's proceed. Let's check the next step. So we will go to the Galaxy tutorial page here. Let's scroll down. Okay, this has already been done. This one has also been done already. Okay, remember when we were performing the mapping, okay, when we were selecting the parameters, there was a part where we had to choose the sorting by coordinates. So that has been done. So the sorting by coordinates involves this and then this. So that has been done. Now let's proceed. So the next thing we'll do is to check the mapping statistics. Whenever you perform a mapping task, it's important to check the statistics. Okay, so we are going to do that as well here on the Galaxy platform. So let's do that and get the statistics. So we are going to get something like this. So let's do it. So here we are going to select some tools flag start. So you say some tools flag start. So it should pop up here. So this is it. So let's click it, and then we will select our data. So we are using this data here, which has already been selected here. And then when you come to the output format, you can decide whichever one you want. Okay, I'll use the text. I'll maintain the text format. And then I'll click on the execute button to get the mapping statistics. So let's do that. Okay, so some tools flag start has been started. So let's wait for the mapping statistics to be generated. Okay, the mapping statistics has been generated. So you can click here and then check it. You can also download the output. So when you come here, click the download button and then save it. So I'll save it. So I'll name it as mapping statistics. So I'll say mapping statistics and then I'll save it. I'll go and then open it on my PC. So this is the file. So I can open it. So let's open it now. Okay, so it has been opened. So we have our statistics here. So I'll focus on the percentage of reads that's mapped to the reference sequence. And we have that here. It is 95.66%. In terms of numbers, this is it. So ideally, we should have majority of the reads mapping to the reference sequence. Okay, and that is what we have here. So things are looking good. Now let's proceed. We'll go back to the Galileo tutorial and then see the next step. Okay, so let's scroll down to see the next step. Okay, so the next step is the variant calling. So we will continue. We should have done alignment cleanup, but we are skipping that because that is not the focus of this tutorial. So take note of that. Ideally, you should do some cleanup and then some quality control, but we will leave that for another day. I have covered some tutorials where I showed how to perform quality control and how to also do alignment cleanup. So I'll leave the links to those videos in the description box for you to check. So we will perform the variant calling. We will use BCFTOOLS. So for BCFTOOLS, we will call BCFTOOLS mpileup first, and then we are going to call the BCFTOOLS call command also. So we will have this first, and then we will have this. That's what we are going to do. So let's proceed. So we will go back to the Galaxy platform here and then do that. So when you are here, you have to search for BCFTOOLS mpileup. So let's search for it. I'll say BCFTOOLS mpileup. So this will bring up the BCFTOOLS mpileup 2. If you don't see it here, just search and then you'll find it. So yeah, so this is it. So we should click it. Okay, so we have our BCFTOOLS mpileup 2 ready. So we will specify our parameters here. So we will start with this one here, the input file. We are going to use the one that was generated by BWMM. So that's this one here. So we already have it. If you don't have it, just click on this browse data set and select the appropriate file. Choose the source for the reference genome. Here, we will keep it at locally cached. Okay, locally cached. And then we will come here to select the reference genome. So let's click and select E. coli, the one we use for the mapping. So we should find it somewhere here. This one. So let's use this one. Okay, so after that, we'll look at another stuff here. Let's check on the index column to see what is there. Okay, I think we will leave this input filtering. I think we will also leave this, but here you can do some filtering. Okay, so if you want to be stringent, you can change some of these options here, but we will leave everything. Okay, we want to use the default settings. Output type, we will maintain the compressed BCF, and that is it. So let's execute this command. Okay, so let's wait for BCFTOOLS mpileup to do its work. So we can see that the job is running now. Okay, BCFTOOLS mpileup has completed its work. Let's move to the next activity. We are now going to issue the BCFTOOLS call command to call the variants. So let's go back to the Galaxy page. So I will search for BCFTOOLS call. So it should show up soon. You can also scroll down to check where it is. I see it here. This is BCFTOOLS call. So I will click it. And then I will specify my data. I'm using the output from BCFTOOLS mpileup. It has already been detected. It has already been detected. So we will proceed. If you don't see, just come to this side, click, and then select the appropriate file. For the consensus / variant calling options, we will use multi-allelic and array variant caller. Then let's scroll down, and then come to file format options. Here we will select a ploid of 1. So when we come to select predefined ploid, we will use 1. So we see 1 because here it's specified as 1. So we will use the same thing here. That is what we have. Let's scroll down. I think so far everything is okay. The output type, we have compressed BCF. We also have uncompressed BCF. So the output type, if you specify compressed BCF, then when you are done, you have to convert it to a VCF format so that you can use it for downstream analysis, especially if you are going to use tools other than BCFTOOLS to process it. Then you need to convert it to a VCF format. You can also use the uncompressed VCF format, which you can also use and later compress it. So it depends on what you want at the end of the day. If you use the uncompressed, that means your file is going to be large. So you still have to compress it. So that's about it. For this tutorial, I would like us to use the compressed BCF formats. So that's about it. So let's run this command. So we will click on the execute button here. So let's do it. Okay, so BCFTOOLS command has been initiated. So let's wait for it to complete its work. Okay, the BCFTOOLS call command has been completed, and that is why we have this output here. So you can click it and you will see this text here. If you take a look at the format, it's BCF. That means that the file is in the BCF format. The size is 24.7 MB. It's very small. The small size is due to the fact that this file has been compressed. The output file here has been compressed. Remember, we selected compressed BCF as the output file type, and that is why this file has been compressed. And this makes it possible for us to quickly download the output file. What we are going to do next is to download the output file. So let's go to the download button here, this icon here. So we just hover your mouse and you see this text download. So that means we can use this button to download the output file. So click it and you will have two options. Either you download the dataset or you download the BCF index. We will download both. The dataset contains the variant information and the BCF index is the index file. So we will start with the dataset. So click on download dataset. Then let's download it. So I will name this as variant.raw.bcf. That will be the name. I'll download the index file as well. I'll say variant.raw.bcf.csi. That will be the name of the index file. Okay, so the files have been downloaded. So let's go and then check them. Okay, so these are the files. This is in the BCF format. If you are going to analyze this file using BCFTOOLS, then you can leave it in this format. But if you are going to use other tools, then you need to convert this file into a VCF format. So what we are going to do next is to convert this file here, which is in the BCF format, to a VCF file. So we are going to use BCFTOOLS to do this. So if you want to follow this part of the tutorial, then you need to make sure you have installed BCFTOOLS. I have tutorials that show how to install BCFTOOLS, so make sure you watch those videos to set up your PC. The links to those videos are in the description box. Now let's proceed. So I'll open my terminal and then continue. Let me do an ls just to make sure I'm in the right directory and I can see my files. So I am going to convert this BCF file into a VCF file. So I'll use BCFTOOLS. I'll say BCFTOOLS view. Then I'll specify the file and then I'll say -OZ. The O should be uppercase. This tells BCFTOOLS that we want to convert this file here into a VCF format and we want the output file to be compressed. That is why we have the Z here. Now let's proceed. We will also add this -O lowercase and we specify an output file name. So I'll say variant.raw.bcf.gz. So this will be the name of the output file. So let's run this command. Okay, we have converted the BCF file into a VCF file. So let's do an ls and we will see the VCF file here. Let's compress. Now let's index this file. So we say BCFTOOLS index. We specify the name. So let's run this command. Let's do an ls again to check. So we will see this index file there. So we are good to go. We can also perform some basic statistics. So that's what we are going to do next. Okay, so whenever you call variant, you can perform the basic statistics just to scan through your result and then you can proceed with the other analysis. So let's perform some basic statistics. We are going to count the number of variants. So to count the number of variants, we can say zgrep-v-c. We indicate a pattern here and we specify the file, which should be variant.raw.vcf.gz. And then we run this command. So this will give us the number of variants. I have a separate tutorial that gives 4 different commands you can use to count the number of variants. So if you are interested, you can watch that video. The link is in the description box. So let's proceed. Now we have the number of variants. We can also count the number of SNPs or indels. If let's say you want to count the number of SNPs, there's a way. If you want to count the number of indels, there's a way to do it. So I'll show you both. So let's start with the SNPs. So to count the number of SNPs, we can say BCFTOOLS, okay, and we indicate SNPs, and we call the file. We add a pipe and we say grep-v. C, we indicate our pattern, and then we run this command. So this will give us the number of SNPs. Okay, so we have that there. So we have the number here. Okay, let's proceed. Let's count the number of indels. So the same command, but this time -v we change to indels. All other statements remain the same. So we specify the file, grep, we indicate our pattern, we run this command. So this will give us the number of indels. That has also been given. If you want the sum of the SNPs and indels, you can do that. So you can say BCFTOOLS view-v. We say SNPs, indels, and we specify the file name. We give our grep command. We indicate our pattern. So this should give us the sum of the number of SNPs and indels. Okay, that has also been given to us. So that's about it. Now let's look at the next activity. Let's go back to the tutorial page. Okay, the next step is to filter and report the SNV variants. Okay, so that's what we are going to do next. This tutorial uses this one, BCFTOOLS.pl. But according to a GitHub discussion I came across, this approach is no longer supported. So I will use a different approach to show you how to filter and report the SNV variant. So let's go back to the terminal. I'll do an ls again just to check the files. What I'm going to do is to issue these two commands, BCFTOOLS view and then BCFTOOLS filter. I'll use these commands to filter and then report the SNV variants. So let's just say we are interested in SNPs and indels. Then what we have to do is to subset. So we are going to identify all SNPs and indels in this file and then put them in a separate file. So that's how we do it, okay, using BCF2. So I'll say BCF2s view. I'll say dash v, I'll say SNPs indels. And then I'll specify the BCF file. And I'll say dash o z. And then dash o again, and I specify name. So I'll say SNPs indels.raw.vcf gz. And then I'll run this command. Okay, so now we have been able to extract the SNPs and indels, and we have been able to store them in a separate file. So do an ls and you'll find file there. Let's index this file. So I'll say BCFTOOLS index, and then I'll say SNPs indels.raw.vcf.gz. So we are going to index this file. So let's run this command. It has been done. So do an ls and you will find another file that ends with CSI. So that is it. Okay, so that is done. Now we are going to count the number of SNPs and indels. We have already done that, but I just want to do it again. So we are going to count that first and then do the filtering and then count again. So I'll say zgrep -v-c. I will indicate my pattern and then specify this file. So let's run this. So this is the number of SNPs and indels. So we'll proceed. We are now going to do the filtering. Okay, so for the filtering, we are going to use this criteria. We are going to filter based on quality. Okay, that's what we are going to do. There are a number of criteria that you can use, but I'm interested in the quality, so I will use that to filter. So I'll use that to show you how to use BCFTOOLS to filter variants. So this is what we are going to do. Let's just say we want variants that have a quality of 50 and above. Okay, or let's just say we want variant that have a quality greater than 50. Let's use that one. So to do that, we will say BCFTOOLS and we say -i. The -i here means we are including this expression, and then we put this in quotes. So we say quality, which is qual, and we say greater than 50. Then we close another quotes. Then we specify the file, which is this one. We can say -oz, and we say -o again, and we say SNPs indels.filtered.vcf.gz. So here I have issued this command to filter, and I want to save the output to this file. Okay, so this will be the output file name, and I'm also going to make sure it's compressed. So I use this one here. Now notice what I have here. This one was SNPs indels.raw.vcf.gz, and now I'm saying SNPs indels.filtered.vcf.gz. So here I have a naming convention. This is raw, this is filtered. So if anyone comes and then take a look at the files, because of the naming convention, that person will be able to differentiate between these two files, because one is filtered, one is raw. So it helps, okay, So you should always have a naming convention that will help you to distinguish between your files. So that's why I have this here, .filter.vcl.gz. So let's run this command. Okay, so it has been done. So let's do an ls and you find the new VCF file here. Okay, you can index it. So let's index it. So you say BCFTOOLS index snaps index.filter.vcl.gz. So let's index this. So it has been indexed. Okay, some BCFTOOLS commands require that you index your VCF file. I repeat, some BCFTOOLS command require that you have a VCF file which has been indexed. So that is why I keep on indexing the files. So now let's count the number of variants in this new file. So we can say zgrep-main-c. We give our pattern, we specify the file name, and then we can run it. So we have this one here. So notice the difference. This was the raw one, the original one, the total number of snips and indels, and after filtering, we have this. Okay, so filtering is important. Okay, sometimes you have this variance, and then it's recommended that you always use high quality snips. Let me just put it that way. It's always recommended to use high quality snips for your downstream analysis, because that will ensure that your results are reproducible and also can be trusted, and the results can be relied upon. Okay, so that is why it's important to filter and select the high quality variant. So this is just an example. You can also filter using other criteria such as the depths and others, but this is something I'm going to cover in detail in another tutorial. So if you are interested in more organized tutorials, then I recommend you check the videos in this playlist. Okay.